Thank you. Thank you, Andreas, for the introduction. Thank you to the program committee for inviting me and to the organization team for putting up such a great event so far. So I was asked to speak at TYPES. I was very surprised because I'm quite an outsider in this community. I was only once at TYPES, maybe you remember, because my talk was kind of cut in the middle by the invited talk. If you were there. Yeah, I decided to talk about something that I'm more of an expert of, that is maybe less directly connected to the TYPES core topics. But I think that would be a fruitful place for exchanges. And so it's kind of a survey of old literature and a few recent papers with these co-authors that I will try to give you an idea of at a fairly high level. So sometimes I try to read model type theory papers because I do model proof theory. And I find it fairly difficult. So I went to the N lab and I looked at what they say for model type theory. Model type theory is a flavor of type theory with rules for modalities. And hence, it's a type theory which, on propositions, reduces to modal logic. So I'm guessing that here modal logic has to be understood with some kind of constructive flavor to it, because it's type theory. And then there is this survey by Alex Cavos, who I believe he wouldn't be very happy for me to cite, but I'm happy to own this sentence for him if he doesn't want to own it anymore. So somehow in the beginning he says that I'm slightly paraphrasing, that work on constructive modal logic starts with Carey Howard. That is lambda calculus that arose as byproducts of the proof theory of modal logic and their associated computational categorical interpretations. So first there was proof theory, and then there was type theory and constructive modal logics. That's an interesting view of the word. So I think what he means here is that in the late 90s, 2000s, there was kind of a boom of papers who considered constructive modal logic from a type theoretic perspective. But what they did is that not that they invented constructive modalities. For the moment, they use constructive and intuitionistic modalities interchangeably. So they didn't start the work on constructive modalities. They took some existing work dating back all the way from the 50s, which were given as sequent calculi and axiomatic presentations, and even natural deduction. But they studied it from a type theoretic perspective, and so they kind of started the cleanup of this theory towards some kind of Carey-Howard isomorphism. In this paper, it's a good example. It's called extended Carey-Howard isomorphism because I also consider categorical semantics. So yes, they use calculi. I just wanted to flash kind of things to this calculus that they use in this paper. They use something that exists. You don't have to read it for now, but it kind of looks familiar to things that you've seen, adding modalities. So some kind of intuitionistic logic plus modalities. Modalities, in my case, will just be box and diamonds, the OGs. And some kind of axiomatic presentation that could look like this. And that's how they start. But then it became something really intricate and a lot of misconception and miscommunication because of name usage and the way that, yeah. So since then, basically this approach, the top approach that was kind of starting from proof theory and developing some type theories from it, has kind of been detached. And so proof theory on these sequent calculi and axiomatic presentations and even natural deduction has progressed in a certain way, and model type theory has progressed in a different way, up to the point that now I can't read model type theory paper very well anymore. And I don't know about vice versa. I should ask these guys, Alex and Daniel. But in one of their recent papers, they actually defined a new constructive model logic from their type theory. And even though I know quite a bit on model logics and in constructive model logics, I cannot really relate their things to my things. So I think we need to bring back the discussion and the cross-fertilization between the two strands. Any questions so far? Yeah. Yeah, sorry. I was meant to say that. If I don't put things on the slide, I forget. So I put at the moment everything in the same bag of like starting from proof theory, developing some type theories, and then getting kind of big. And so Penning-Davis, where at the start of it, it's just using a kind of starting point that is different and that has S4 instead of just plain basic model logic. Yeah, don't put all the references. Kind of just give some sort of narrative. Right. So as they put it in their own paper, they started with relatively well-known axiomatic systems and calculi. So I'm going to give you an idea of what now, several years later, what this would mean. This phrase would mean now in my eyes. Then we want to axiomatize some kind of constructive intuitionistic model logic. We can start with just an axiomatization that is like classical model logic, but just with an intuitionistic propositional base. But that obviously doesn't tell us anything about the diamond modality, because in classical logic, box and diamonds are dual, but here we don't know anything about diamond when we write this. So that's the starting point. It's sometimes called in the literature little ik. Then no. Dual as diamond A is not box. But they are not. But in this context, they are not. Yes. Sorry. In principle, like disjunction and conjunction are dual.
Because they're all the term of the negation.
No, I don't. It's a little bit not the things that I know, but I think box and diamond are not left and right adjoints, not this diamond.
Yeah.
And an or.
Just
and an or, yeah.
The appropriate things box and diamond are also built more than not. So I didn't mean to give you a the question. So
I'm not saying that they are monads and comonads. I'm starting from a much more basic point.
Just clarify what exactly mean by reality, and I understand.
Yeah. So I meant but the fact that diamond A is not box, not A, and this is not the case here. And therefore, when we only have axioms that talk about and rules that talk about box, we don't know anything about diamond. So as I quickly showed before, but you weren't expected to read it, the kind of natural pendant to the first axiom is this kind of monotonicity of the diamond operation. And that's now usually called CK logic. And then something that is true in classical model logic is that not only the box, but also the diamond is normal, so it distributes. So box distributes over conjunction and diamond distributes over disjunction. So one axiom that is possible to add expressivity to your diamond is to say it distributes over empty disjunction, or it distributes over non-empty disjunctions, binary disjunctions. And so this increases the logic little by little, and then there is something called Intuitionistic K, which takes these five axioms. And they have been devised by several authors through kind of refinements of axiomatization. So that's what is now a relatively well-known axiomatization. And so because it's, I believe you agree with me that it's easier to read things when they are written as inferences, we can kind of try to work our way through correspondences between axioms in the axiomatic presentation and sequent roles. So I didn't say, but a sequent like gamma arrow A, like on top of this inference, I read as the disjunction of gamma implies A. So this is the rule that is sound complete with this. If you add to an intuitionistic base calculus, if you want to go to CK, namely adding this axiom, you can add a similar rule to it. When I write box gamma, I mean box B for every B in gamma. Now something that's probably a bit less expected is we can also tackle this distributivity over empty disjunction by just allowing, instead of a single formula on the right, at most one formula on the right. And that will give us a sequent calculus for this CK plus K5 logic. I know that the name of these axioms make no sense, but somehow that's what I ended up with, and didn't want to change it and forget to change half of the slide and then create more confusion. So we're stuck with that. Okay, now we want to have something to say that diamonds distribute over binary disjunction. And so we could think, why not play a similar trick? Before it was empty disjunction, I had an empty right-hand side. Now I have more than one formula in my disjunction, so I could have more formula in my right-hand side. Unfortunately, this is too simple. It doesn't work. It's complete with cut, but it's not cut-free complete. This is an example, no need to read it. So it's not cut-free complete, so scary. Right. Any questions so far? Yes.
Are the complex or other sets like a real over complex?
Sorry?
Sorry, the gammas, are they really reorderable?
Yes, they are Merle sets. Yes.
Your definition of cut is the second calculus one, not
Yes.
that.
Yes. Yeah, I'm in sequent calculus. I didn't want to introduce natural deduction as well, so I decided it was close enough that you could kind of squint your eyes and understand what I mean. Yes.
What's your intended intuitionistic interpretation of the diamond?
Sorry?
What is your intended intuitionistic interpretation of the diamond?
That's a very good question. I am not saying it yet. I'm keeping it vague because I'm just saying we know what diamond means classically, and we are trying to get a diamond constructively, and depending on how you pick and mix your axioms, you will get different diamonds. But because I haven't given you any semantics or anything like that, you can't really feel what the different ones are. But at the moment, they're just given by these axioms. That's it. Yes, so box is the restriction of the universal quantifier, and diamond is the restriction to the existential quantifier. Yes, but also in terms of just direct translations called Sanders translation into first order language. So it's really just a restriction to a relation. Yeah, use the relation in your language. Yeah. Yeah, so because I started with model type theory, and the systems given by model type theory don't satisfy that.
Intuitionistic predicate, but it's the same, right?
Yeah, I agree.
Yeah.
But apparently these other guys, they don't agree. Or at least that's not what they're doing.
All the same time, like Alex is a diamond saying that it's contravariant and like they won't get very good.
Yeah.
So,
Did I miss someone? No, okay. Right, so another discussion that I had with Alex, like back in 2017, he was saying like, why should we even look at diamonds? Diamonds mean nothing. And at the time, I didn't have a proper answer, except that I liked the diamonds. And also that these early papers like Fanning and Davis or Bailey and DePaiva, they do consider the diamond. They don't ignore it. So they were interested in it at the time. It's always hard to like recover history from just literature. But now I have a different answer. So one of the reasons people thought that diamonds are not so relevant is because they thought that at the end of the day, if you looked at only the diamond-free theorems, which they thought were the only ones that made sense, that they could understand the box and that's it, then in all these logics, they were all the same box theorems, box validities. And it turns out that some people knew it, but it's not the case. They don't coincide. So that's another reason to understand the diamond, because actually you can get more box validities by adding certain diamond axioms, which is quite surprising, maybe. So the different results are that if you take CK, so K1, K2 plus K3, K4, this is a box conservative over the smaller box fragments. Same for K3, K5, but on the other hand, CK plus K4 plus K5 is not conservative. It has more box theorems than, even though the axiomatization for the box is the same if you just look at the axioms. And there are some questions that are unresolved as of yet. So I think I'm probably quite slow, so sorry. So these two results, we proved one of them in a fairly complicated way, and then someone observed that it can be obtained very simply by just translating. If you look at the axioms, these axioms, and you translate all the diamonds into top or all the diamonds into bottoms, then you get certain theorems of intuitionistic logic, and it just collapses. And so you know that you realize you have no more theorems on diamonds than you had without those axioms, if you just collapse them. Yes, so that was an observation by Tim Lyon, and then extended by Anupam Das. So our complicated proof was not necessary for that. So that's the blog by Tim Lyon, where the discussion occurs about this simplification of the proof. So it's Q. And but then we have the non-conservativity result of this other one, this other combination of axioms. And this we obtain as a corollary of a Gödel-Jensen negative translation for this logic. What does it mean? If you translate the formulas using double negation on the positive connectives, then you can translate every theorem of the classical modal logic as a theorem of this intuitionistic logic. And in particular, you have this specific theorem, not box bottom implies box bottom, which is a theorem of that bigger logic and not of the smaller fragment, which people thought was the diamond-free fragment of all the logics. So this is why I think we should consider, we should at least pay a little bit of attention to these subtleties around diamonds. But then coming back to my earlier point, we still are stuck with no rule for diamond that goes beyond the nullary disjunction distribution. So that's where another point about modalities in proof theory comes, which is that modalities need structure. Any questions at this point? Have I lost you?
When you say the diamond A can be considered to false,
Yeah.
but then you have the axiom which says something that diamond produces is false.
Yeah. You don't translate that one, so you only translate the ones that you need. So when you do the first one, you only translate K3 and K4. And that's when you do diamond A to top. So you don't prove top implies bottom. It was not into that logic yet. But then in the second one, you translate it to bottom, and then obviously you have bottom implies bottom. Yes. Yeah, I went quickly because I think, yeah, we can discuss the details. Right. So what do I mean by this? Well, first of all, in this evolution that I described, both in the time theoretic side and the proof theoretic side, we have observed just a development of systems that take care of modalities, and they all have some kind of structure to it. There are things that are called nested sequence, dual context systems. In the paper that I cited by Carvos and Ratzer, they have something called locks and keys, something called prefix tableau from the 70s. So all of these, they just add some kind of structure to their language to be able to have a good form of modalities. So we must conclude that these modalities then with structure. And yeah, so this is basically the idea that has kind of made this development go much quicker and further. And we can kind of abstract a lot of these structural elements in the language and relate it to the semantics of modalities, which is given by Kripke as a relational semantics. So it's just a graph, a simple set of nodes or words, and then some arbitrary relation on them. And then each word you evaluate your propositional atoms, and that gives you a semantic for your modalities. And as I briefly mentioned before, the box is evaluated at a word, looking at all the words that are accessible in one step. And if all of them satisfy the formula, then box A is true. And diamond is the equivalent for there exists. So that's in the classical word. When we have this duality that diamond A is not box, not A. And so one specific way of adding structure to the syntax is by just encoding all these elements. And so we can add, so instead of having sets of multi-set of formula gamma, arrow multi-set of formula delta, we add this R, which will contain the relational structure of a graph, written as X, R, Y for each edge, and then each formula will be labeled by an X, depending on which will relate to like the valuation, because that's the information at work basically. And then again, that's in the purely classical way, but it's just easier to read this way. You can have rules that are now acting on these labeled formulas and using the context to carry the information about the relation. So to conclude, on the right, that box A at X, we have to introduce a fresh variable Z, a fresh constant, such that XRZ, which is part of our relational context, and then Z at A at Z. And this really mimics what you would do in first order logic if you were just reading that semantical clause. And you do the same for the diamond, and you do the same for left rules and all the propositional reasoning happen at a word. So you just have annotated. If you want the rule for implication, you will have A implies B at X, and then you have X A X B. The propositional reasoning happens at a word. Yeah.
Okay, now
yeah.
That X colon box A feels a lot like what the
No, it's just a constant. It's a constant that talks about the graph.
This X can be colon many things, but
yeah, but X is X. Yeah. You only have these kind of labels that they are not really variables because they don't get instantiated by anything. They're just this kind of constants represented your nodes in your graph. But sometimes when you want to say that box A, because you want to look at all the possible ones, you introduce this kind of arbitrary one like you would do in mathematics. Right? If I have a fresh one, it must be true for that one.
Sorry, missed it when you said this. So from the very multi including factors, they are back to classical?
Yeah. This is classical. Yeah, sorry, I turned this a lot in my head, but I thought at this point I have to just explain the classical case just because it's easier to read and we can go faster for the constructivization. Other questions? Yes, so here we can then have a standard soundness and completeness, and obviously the soundness with respect to the graph models is going to be fairly easy because the graph models can be read from the syntax now. Okay, so that was what is done in classical model logic, and so what would be your first guess if you had to make it constructive? Single conclusion version of that. Yeah, I don't think we need at most one. I think single conclusion is enough.
what did they mean? I mean, as I suggested, just the empirical logic translation of what to do, what's wrong with it?
No, that's exactly what it does.
And that's a simple solution. That's
I agree, and that's yeah, but that's fine. That's yeah. That's fine. That's exactly what it does. Yeah. So then you want to understand the expressivity because here I'm talking about basic logic. Then you might want to talk about transitive frames or other extensions that you want to kind of see how this plays out. But yeah, as a basic logic, if you just do the same thing exactly, let's start with this. And here I didn't write the semantic clause because now the semantic would be different. I just wrote the translation in the first order language. And indeed, just reading this, like you say, like a first order formula, you unfold this formula into your first order system, and then you read off that rule, one formula on the right. The key thing is still that the for all quantifier, the universal quantifier, does not have the same meaning in the classical and the intuitionistic word. But once you're restricted to one formula on the right, you have the correct meaning. Yeah.
I mean, you could get not for all is the same as system.
Exactly. You get the same non-duality that you have in between.
I mean, indeed, the duality, classical duality is misleading. Negation is generally the population. Only the duality in terms of attraction, which should be what appears to be theoretically really. I never understand this. Why this focus on negations?
Sorry?
I'm out of question.
Oh, you're out of question. I mean, that's a bit rich for you to say, yeah, Gabrielle. Yes, so same thing. Restrict to one formula on the right. And okay, but then the question is, which logic do you get? So actually, I should have put back my square picture, because if you go back to my axioms, so when we were talking about the sequence calculus earlier, we had kind of these things where we were playing. We could say, if I want this axiom, if I want that other axiom, and then it breaks down, and then now we're going straight to IK, the full set of axioms, the complete axiomatization, and that's what is. So you're losing any modularity here. This is the logic that you're given. We saw that IK was not box conservative over CK, the smaller logic. So that means that here, when you prove box theorems, you're hiding some diamonds somehow in the structure. The structure is giving you more and is providing you these extra diamond theorems. So yes, you could say that you're losing a bit that, yeah.
There are combinations of intuitionistic logic that multi-successors work together your holding. So I would say that in the two-level presentation, that are intuitionistic, if you exchange the word on arrow molecule or something like that. And I wonder if people have tried that actually.
So I'm not sure I will have the time to get to that, but that's the last part of my talk. But I think I have 10 minutes left, right? So, yeah. Yeah. And their logic is IK. Yeah, absolutely. So, as I say, it's just the first attempt. They have a different usage of labels, but I don't have time to get into that. You can ask Elaine or me, because we have this work that studies that. Right, so some pros and cons of this first system. So you have this direct connection with the standard translation. And actually, this was Simpson's idea. So that exactly like Thorsten has been saying since the beginning, why don't you just do the first order thing? Why do you bother with all this? And Alex was exactly saying that. He was saying, like, I want an intuitionist, I want constructive reading of the standard translation. I want a system for that. And ideally, I want to do everything constructively, but the completeness is not constructive. So that's great. This is not something we had before, because we were missing some diamonds there. And it's fairly manageable. And one key thing is that it's easy to extend. So if you want to talk about transitive models, you can just add a rule for transitivity. So you can see, because you have this direct access to these relational context, you have something that says X are Y, Y are Z in your conclusion on the left, then you have X are Z in your premise. And just like that, you can talk about transitive models, and you can derive this theorem now.
Just a quick comment on that, the translation. If you do that in the intuitionistic case, you only have the outcome to give
Yeah.
it. If you try to do that with CK, for example.
No, exactly. That's the whole point. Yeah.
Have less axioms than the 5.
Yeah, exactly. The standard translation, which is this translation into first order logic, it just gives you this full logic, and like you said, maybe that's the right, because of that. That's Alex Simpson's point, that this is the right logic because you recover an intuitionistic reading of the standard translation. But all the other model type theories don't do that. And then the thing we've done recently is that if you take this system where you talk about transitive models and you actually look at infinite proof trees, so co-inductively defined proof trees, not inductive objects, not finite trees, you can actually characterize an intuitionistic version of the GL logic, the Gödel-Loeb logic, which characterizes transitive and terminating models. And you can prove this statement now, which has been studied as a form of recursion in some systems, if you've seen that before. I don't have time to explain the details. One little difficulty, and that's Alex Simpson spends a lot of time in his thesis on this, is that this is not in direct connection with the semantics for intuitionistic model logic. And now I'm going to be very, very quick. Why would you want to have this direct connection with the semantics that I have not yet introduced? One reason could be because if you want to decide your logic, you want to be able to use your proof system to decide your logic. Say you have a formula, you want to know whether it's valid or not. Apply your proof search. If you find a proof, great, the formula is valid. If you don't find a proof, well, for it to be decidable, you need to be able to say something there. So you want to be able to find a countermodel. So you want to be able to finitize the proof search, terminate it, and then extract the countermodel. And the closer your syntax is from your semantics, the easiest that would be. So now, so I introduced the relational semantics for model logic, and then Kripke, they like extended this or expanded this to also cover intuitionistic logic, which I believe most of you are familiar with, where the relation is not arbitrary, but it is a preorder. And the valuation is not arbitrary, it is monotone with respect to that preorder. And that's a way to interpret the implication with respect to upward sets. And so you could do the same game as using some sort of preorder labeled atoms, labeled sequence to describe intuitionistic logic. So the same way that I was using the relational model of relational semantics to encode my modalities, I can do the same for the implication. And I also need to encode the preorder properties. But like I said, these systems are easy to extend. So you just add the reflexivity and transitivity into your context, and that's easy. And you get a different system for intuitionistic logic, which is sound and complete. And that can give you a second way to constructivize your original label sequence, which is by going to a semantics that's been around for a while, before all of these developments, which says that you can interpret intuitionistic model formulas if you have both relations in your graphs. So now you have a birelational graph with the preorder relation and the original accessibility relation, and the valuation must be monotone with respect to the pre-order like before, just to interpret the implication. You have some confluence conditions. Someone told me it shouldn't be called confluence. And then you can do the same game where you have both atoms in your language. You can rewrite your rules with just even more syntax, adding all the conditions that you need. And that gives you more expressivity because you have more fine-grained tools to play with, and also something that is closer to the semantics, which lets you do the proof search decision procedure that I described in a very simple way. So that's kind of a decision to the user which system, like the easy, light one, or the more heavy, even more expressive one. And I wanted to mention, I'm done. I just wanted to mention that there is a lot of work going on in this area at the moment, some relating to other systems or other semantics, how they all relate, because like there are a lot of gaps in what I explained so far. Yeah, thank you very much.